In this fifth module, we are discussing the structure of hadrons and strong interactions. In this second video, we discussed the inelastic scattering between electrons and nucleons and what one can learn from that. After following this video, you will know about resonances as excited states of nucleons, deep inelastic scattering and nucleon structure functions, and the so-called scaling hypothesis as evidence for substructures inside the nucleon, as well as the role and distribution of quarks in the nucleon. Form factors decrease rapidly with Q2, like we showed in video 5.1. Consequently, the probability to observe an elastic scattering becomes low at high energy momentum transfer. This is not surprising. Larger Q2 correspond to a short photon wavelength, which is then more and more able to resolve the internal structure of the target particle. This structure will then not be insensitive to the energy momentum transfer. The target will be excited or even destroyed. In other words, inelastic processes take over. At moderate Q2, inelastic processes produce excited states of the nucleon, also called resonances, such as delta plus, which have the same quantum numbers as the proton. These resonances have an extremely short lifetime and therefore a broad mass distribution. The figure shows the result of an electron-proton scattering experiment at an energy of about 3 GeV and at fixed scattering angle. The inelasticity of the reaction is first visible in the energy distribution of the outgoing electron on the left, which is no longer fixed as in the elastic case. Broad secondary maximum are formed, which correspond to excited states of the nucleon, also clearly visible in the invariant mass distribution of the outgoing hadronic states on the right. Its kinematics is completely determined by measuring the outgoing electron, as in the case of elastic scattering. The position and the inverse width of the large maximum indicate the mass and the lifetime of the resonance delta plus 1236. At higher Q2, beyond the resonance region, we enter into the region of the so-called deep inelastic scattering. The final state consists of multiple hadrons with at least one baryon to conserve quantum numbers. This is the region where the photon interacts individually with the charged constituents of the nucleon. The cross-section can be parameterized with two terms as before, but with two unknown structure functions, W1 and W2, replacing the form factors. They parameterize the distribution and dynamics of the nucleon constituents. They depend on the transferred energy nu, which is the energy of the photon, and its invariant mass Q2. The kinematics now requires a second additional kinematical parameter, because of the mass of the hadronic system is no longer fixed, as was the case with the proton or resonance in the final state. In addition to the scattering angle, we can thus choose a second variable. Here is the energy A' of the outgoing electron. The structure functions are measured experimentally, analyzing the dependence of the cross-section on the scattering angle, like in the elastic case. The big discovery at SLAC in the late 60s was that the structure functions do not depend on nu and Q2 separately, but on their ratio xbj, which is equal to Q2 over twice the mass of the proton times nu. The variable is named after its inventor, James D. Bjorken. The phenomenon was called scaling at the time because of the very general observation that the dimensionless variable xbj does not depend on any energy nor mass scale. Structure functions follow in fact scaling if inside the nucleon there exist substructures with which the photon interacts elastically. This interpretation of scaling is best demonstrated in the limit of large Q2, where the interaction between quarks is negligible compared to the force transmitted by the photon. Quarks then act as quasi-free particles, with which the photon interacts in a coherent manner. To respect kinematic constraint in such elastic electron-quark scattering, the photon can only interact with a quark which carries a fraction xbj of the nucleon momentum. Consequently, the cross-section is proportional to the probability to find such a quark in the nucleon. In the limit q square going to infinity, the structure functions w high tends toward the function f high x, which are directly related to the distribution of the fractional momentum xi carried by quarks of type I. The experiments at SLAC have in fact shown that the phenomenon of scaling already occurs at a moderate q squared. The structure function W2 as a function of the kinematical variable omega, which is about equal to 1 over xbj, smoothen with increasing q square beyond the resonance region, and then follow a universal function of xbj independent of q square. The kinematic constraint imposed by elastic scattering of point-like particles inside the proton is indeed respected. However, the scaling of structure function is not exact. This figure shows modern measurements that come from experiments at the electron-proton collider era. The curves and data for different x are displayed by the constant in order to be all visible in the same graph. At small x, so at small quark momenta, the structure function varies strongly with q square because of the contribution from virtual gluons enriching the quark contents. The smaller deviation at large x are more subtle. The coupling constant of strong interaction depends on the momentum transfer. It is not really a constant. We will come back to this astonishing fact in video 5.4. Structure function can thus be used to measure the momentum distribution of quarks inside the nucleons. We qualitatively demonstrate the behavior of the structure function f2 of x based on successively refined hypotheses on the dynamics of quarks. If the nucleon consisted of 3 quarks without interaction, x will be fixed to 1/3 for each quark, and f2 will be a delta function at this value. If it were a state where quarks are bound together by gluons, the average value of x will still be 1/3, but with a wider distribution around this value. If we finally take into account that quarks can emit virtual gluons which can split into a quark-antiquark pair of low energy, we expect that the quark momentum distribution tends to fill up at x going to 0. The experimental data indeed follow this qualitative picture. For so-called valence quarks, that is, the 2 up quarks and 1 down quarks for the proton, the structure function varies around 1/3, with a strong enhancement at small x by additional quark-antiquark pairs produced by gluons. The integral of the distribution is twice as large for the up quark than for the down quark, as it should be. The contribution of gluons is indeed seen in the contribution of s and s bar quarks, which would not be present in the nucleon otherwise. When integrating this distribution, we see that only about 1/2 of the proton momentum is carried by quarks. The rest is carried by gluons. In the next video, we discuss mesons, bound states between quarks and antiquark.